In this video, we are going to explore something that plays a major role in handling massive amounts of real-time data, column-oriented NoSQL databases, with a focus on Apache Cassandra. Now, let's start with a quick scenario. Imagine you are building a system like Instagram. There are millions of users uploading content every second, and you need to store, retrieve, and update data extremely fast across different locations around the world. Traditional row based databases just can't keep up with that level of scale and speed. They get bogged down when working with datasets and white tables. So, what's the alternative? That's where column oriented databases like Cassandra come into the picture. They are built for high write throughput, horizontal scalability, and low latency, even with petabytes of data. So, in this video, we will understand what a column oriented NoSQL database actually is, how Apache Cassandra works, and why it's used in real world large scale systems.
Thanks, Chaitanya. Let's dive right into it. So, what is a column-oriented NoSQL database? In traditional relational databases like MySQL, data is stored row-wise, meaning all the columns of a record are stored together. That works fine for small to medium applications. But when you're dealing with the massive data and you often need to query specific columns only, this approach becomes inefficient. Column-oriented databases like Apache Cassandra flip that model. They store data by columns instead of rows. This means data for each column is stored together. It is optimized for faster reads and writes on specific columns across huge datasets, which is ideal for use cases where you are aggregating or filtering by certain columns frequently. How Apache Cassandra works. Now let's talk specifically about Apache Cassandra, which is one of the most powerful column-oriented NoSQL database. Here are its core features. Distributed architecture. Data is automatically distributed across multiple nodes. It can scale horizontally, meaning you can just add more servers to handle more load and no downtime required. Second is peer-to-peer model. Unlike traditional master-slave databases, Cassandra uses a peer-to-peer model. Every node is equal, so there's no single point of failure. Tunable consistency. You can decide whether you want to strong consistency, eventual consistency, or something in between based on your application's needs. Fourth one, high availability. Even if some nodes fails, data remains available due to replication across datasets.
In this part, we are going to talk about how Facebook Messenger uses HBase for real-time messaging. Every second, millions of people send message on Facebook Messenger. But have you ever wondered how these messages are delivered instantly, even when billions of users are chatting at the same time? Traditional databases like MySQL struggle with massive volume of messages. They face slow performance, high storage cost, and difficulty in scaling. Facebook needed a better solution. To handle billions of messages efficiently, Facebook adapted HBase, a column-oriented NoSQL database that provides high-speed write, scalable storage, and real-time access to chat history. Here's an explanation of how it works. Imagine millions of Facebook users sending messages at the same time. Each message is a request that hits the backend system simultaneously. But traditional relational database can't keep up. As user traffic explodes, they struggle with performance bottleneck and limited scalability. This system weren't built for this kind of volume. As a result, they hit a wall when trying to scale out message storage and retrieval efficiently. To solve this, Facebook turned to Apache HBase, a distributed NoSQL database built for handling massive amount of data across many servers. Instead of collapsing under the load, HBase thrives with parallel requests. Each user's chat thread is stored as a row, and every message becomes a column within that row. Here's how it works. A given thread, say thread 1234, message from user A and user B are stored in separate column along with a timestamp. This structure allows messages to be written and read in real time at scale. By switching to HBase, Facebook unlocked high-speed, scalable storage, making Messenger fast, reliable, and ready for billions of conversations. HBase stores each chart as a row. Messages saved are saved as a column. Allow for fast retrieval of chart data. Ensure efficient data flow from memstore to HDFS. It delivers fast read and write for real-time charts. It automatically scales as the user traffic grows, and it ensures seamless message retrieval even after years later. Thanks to HBase, Facebook Messenger can deliver message instantly no matter how many people are chatting. Column-oriented database like HBase powers the app we use every day.
So let's talk about HBase architecture. HBase has two types of nodes, master and region server. There is only one master node running at a time, whereas there can be one or more region server. The high ability of the master node is maintained by Zookeeper, a service for distributed systems. The master node manages cluster operations such as assignment, load balancing, and splitting. It is not a part of the read or write path of data. The region server, it has one or more region server running at a time, posts tables, performs read and write of the data. Clients communicate with the region server in order to read and write their data. A region in HBase is the subset of table rows. The master node detects the status of region server and assigns regions to it. Let's talk about HBase components. HBase components. The image represents the HBase components, which includes HBase master and at the bottom of multiple region servers. The HBase master is responsible for the management of the schemas which is stored in HDFS. Region servers acts like ability servers that enables the maintenance of a part of the complete data stored in HDFS. Based on the requirements of the users, the region servers performs this task by using the H files and the write ahead long or WoW service. The region servers always stay in sync with the HBase masters. It is the Zookeeper that makes the region server perform a stable sync with the HBase master.
Moving on to storage model of HBase. The two major components of storage model are partitioning and persistence and data availability. First is partitioning. Partitioning is one part of the storage model where a table is horizontally partitioned into regions. Each region is composed of a sequential range of keys and then managed by a region server. A region server may hold multiple regions. Second is persistence and data availability. They are also important components of the storage model. HBase stores its data in HDFS. It does not replicate region servers and relies on HDFS replication. For data availability, the region data is first cached in memory. Updates and reads are then served from the in-memory cache, which is called the memstore. Periodically, the in-memory cache or the memstore is splashed back to HDFS. The val stored in the HDFS is used for the durability of the updates. Moving on to row distribution of data between region servers. The image describes the distribution of rows in a structured database using HBase. It shows how the data is sliced and then maintained in individual region servers depending on the requirement of user. This type of distribution ensures availability of data for a specific user. As you can see with the data A1 through Z55, some data is split based on the index value. For example, null to A3 is in the first region server and A3 to F34 is then stored in the second region server and so on. Moving on to data storage in HBase. Data is stored in files called the H files or the store files that are usually saved in HDFS. An H file is a key value map generated due to the MapReduce operations that are performed by ADO. When data is added, is returned to the WAV or stored in memory, this memory data store is called the memstore. H files are immutable since HDFS does not support updates to an existing file. To control the number of H files and keep the cluster well balanced, HBase periodically performs data compactions across the HDFS cluster. Thank you.
Let's explore how data is written in Apache Cassandra. Step 1. Writing data to memory, mem table and disk, that is commit log. When a write request arrives, Cassandra first writes the data to two places simultaneously, that is mem table and commit log. Mem table is an in-memory data structure that temporarily stores write for fast access. Commit log is a persistent log stored on disk, ensuring durability in case of a system failure. Step 2. Flushing mem table to SS table. As more write accumulate, the mem table goes. Once it reaches a threshold, it is flushed to disk as an immutable SS table, that is sorted string table. This process also includes an index for faster lookups. This approach makes Cassandra highly efficient for write-heavy workloads, ensuring data consistency and durability while maximizing performance.
Hey everyone, I am Ritesh and in this video we are diving to an exciting topic from the world of distributed database. Modern advancement in Cassandra, especially focusing on lightweight transaction or LWTS. Before we go technical, let's talk about why this is important. Imagine running an online store during big sales and you have just one unit of product left. Two customers click buy now at the same time. What happens without proper control? You might be end up overselling, which damage trust and create operational issues. This scenario demands strictly consistency, and that's not something NoSQL database like Cassandra were designed for. Cassandra is known being for highly available and scalable, but eventually consistency doesn't always cut in it this real-time critical use cases, and that's exactly where lightweight transaction comes in to bridge the.
Thanks, Ritesh. Alright, so let's break it down. Cassandra is a distributed NoSQL database that's optimized for write heavy workloads and global scalability. But when we need strong consistency for certain operations like preventing duplicates or ensuring only one update goes through, we use something called lightweight transaction or LWTS. So, what's exactly is a lightweight transaction? In simple terms, we can say that it's a compare and search operations. You tell Cassandra to write data only if a specific condition is true. Here's an example. Let's say a command called as insert into users username email values ritesh123 ritesh @ gmail.com if not exists. This checks if ritesh123 already exists. If not, it proceeds. If it does, the transaction is skipped. It's all handled behind the scenes using a consents protocol called Paxos, which ensures agreement across nodes before applying the change environments more confidentially. Where can we use LWTS? LWTS are perfect for ensuring unique usernames during registrations, handling financial transaction, managing inventory counts in real-time applications, preventing duplicates entries or race conditions. Basically, anytime you need only one winner is a concurrent scenario, LWTS have your